Hi everyone, my name is Minh Tran, and today I'm going to talk about a scheme to protect digital quantum simulation against the violation of symmetry. This is a joint work with Yuan, Dan Carney, and Jake Taylor, and it is based on a published paper. So the aim of digital quantum simulation is to simulate the dynamics of a quantum system on quantum computers. For example, if we have some interacting spin that are described by a Hamiltonian H, then the first thing we should do before we simulate this simulation is to map these spins onto qubits on a quantum computer. We will then use some elementary quantum gate of the quantum computer to simulate the dynamics of the system. The approximation of the dynamics of the system by these quantum gates, they introduce some error in the simulation. And normally these error, they only deviate the simulation from the ideal evolution. So you may get some incorrect results, but if you have a good algorithm, then these results are just slightly incorrect and you still learn something about the ideal evolution. But these errors, they may also violate the symmetry of the target system. And what you end up with is some state that doesn't even obey the symmetry of the system. And these are sometimes unphysical results that you don't know how to explain in your theories. So here's a thought. Instead of letting the symmetry being violated by the simulation error, can we actually use the symmetry of the target system to suppress the simulation error? And the answer is what we call a symmetry protected simulation. For that, we make a few assumptions about the system and the simulation. First, we assume that the Hamiltonian has a symmetry S, that is a set of unitaries U, such that every unitaries U in the set, they commute with the Hamiltonian. We also assume that we're gonna simulate this evolution under H using an algorithm that first divide time into many small time steps and then approximate each time step by a quantum circuit, C delta T. An example of such an algorithm is the first order trautorization, where we divide time into many small time steps, and in each small time step, we approximate the evolution of the Hamiltonian by the evolution of under each term of the Hamiltonian. And that's why we call a raw simulation, where we just repeat the same circuit many times. In a symmetry protected simulation, we're gonna insert between these circuits the unitaries that are drawn from the symmetry S of the simulation. For example, we're gonna sandwich the first circuit by some unitaries U1 that are drawn from the symmetry S, and same with the next circuit, next implementation of the circuit C delta T, and so on. The reason why we do this is because we can think of the circuit as the correct simulation, correct evolution under the Hamiltonian H plus some error. Now, because we chose these UK from the symmetry of the system, they commute with the Hamiltonian. So these unitaries UK, they do nothing to the correct part of the evolution. And the correct part of the evolution remain unaffected by this UK. But the error part of the simulation, they may not commute with this UK. And in fact, these are the part that are responsible for the symmetry violation in the system. So they can be manipulated by the symmetry transformation UK. And the aim of a symmetry protected simulation will be to choose this UK in a way such that we can manipulate these, we can suppress the error of the simulation. Here's an intuition for what happened when we apply the symmetry transformation to the system, to the simulation. In a raw simulation, we just repeat the same circuit many times. And if you think of the error in one circuit as a vector in the space of operator, then what happened is that the total error at the end of the simulation will be just the sum of these vectors. And that's why we get a large error at the end of the simulation. But in a symmetry protected simulation, these unitary UK that we insert in between the circuit, what they do is that they rotate the arrow in one shorter step by some random angle. And when we add this arrow up at the end of the simulation, this arrow, because they are now pointing in different directions, they may cancel each other out, and we end up with a smaller arrow at the end of the simulation. More rigorously, the total arrow in a raw simulation, they typically scale as the number of shorter steps multiplied by the arrow in one shorter step. And we can show that in a symmetry protected simulation, the total arrow will still be the number of shorter steps, but now multiplied by an average version of the arrow in one shorter step. And this is the average under the symmetry transformation UK. And you can see that if we choose this UK in a clever way, such that this average is much smaller than the arrow in one shorter step, then the total arrow in of the simulation will be also much smaller. Let's consider one simple example to demonstrate how this symmetry transformation work. And in this case, we consider this Heisenberg interaction between every spin on a lattice. XX, YY, and ZZ here are just Pauli matrices, and the Jij, they are just coefficients that represent the interaction between the spin I and J. This Hamiltonian is SU2 invariant in the sense that if you apply the same single qubit rotation on every spin, then you will end up in the same Hamiltonian. And we're gonna use that symmetry to protect the simulation of these Heisenberg interactions. On the algorithm side, we're gonna use the first order factorization, where we divide time into many small time steps. And then in each time step, we break the evolution under H into the evolution under the X term, the Y term, and then the Z term. And you can also notice that when we break the evolution under those under X and Y and then Z, the right-hand side no longer respect the SU2 symmetry. And this is the source of the symmetry violation in this simulation. We're gonna look at the total error of this simulation as we increase the number of shorter steps. Remember that when we increase the number of shorter steps, delta T also decrease, and we expect a smaller and smaller error. We can also get the error in one shorter step. To the lowest order, this error will be proportional to the commutator between the terms of the Hamiltonian. In a raw simulation, because the error in one shorter step, it decreases as 1 over r squared. And because there are roughly r step of the simulation, the total error will be 1 over r as expected. And in a symmetry protected simulation, and here we choose this symmetry protection in a random way. We choose this single qubit rotation randomly according to the Ham measure. And the idea here is that in every step of the simulation, the error of the simulation will point to a random direction. So when you add this arrow up, the total length of this vector will be roughly square root r multiplied by the length of one vector. And here the length of one vector, it decreases as 1 over r squared. And that's why we get the scaling 1 over r to the 1.5. Instead of choosing this UK randomly, we can also look at the structure of the arrow in one shorter step and choose this UK in an optimal way. And in this example, if you sandwich the arrow in one shorter step in between the Hadamard gate, then you will induce a minus sign in front of the arrow. So that's what we're gonna do for an optimally chosen symmetry protected simulation. We're gonna insert Hadamard gate in between the step of the simulation. And what happened is that the error to the second order will vanish every 2 shorter steps. So the total error in the worst case, it will be just the error in 1 shorter step. And that's why the error in this simulation, it scale as 1 over r squared. There's also the simulation of lattice gauge field theories, which is a main target of our symmetry protected simulation scheme. This model, they describe the interaction of particles and fields in physics. And in this model, they test the Gauss law that constrain the relation between the particle number and the field. And more mathematically, this Gauss law, they can be represented by this gauge operator that commute with the Hamiltonian. And they form what we call a gauge symmetry that the system has to respect. But in a digital quantum simulation, because of the shorter error, this gauge symmetry may be broken, and we end up in the final state of the simulation that sometimes violate the Gauss law, that are not, so such a simulation are not allowed, such a final state are not allowed in nature. And we're gonna apply the symmetry protection to an example that is a stringer model. And in particular, we're gonna implement the simulation of the stringer model in the proposal by Shaw and others in 2020. We're gonna look at the leakage to the unphysical subspace during this simulation. The leakage here is basically the fraction of the state of the system that leak to the unphysical subspace. Then you can see that in a raw simulation, the leakage grow with time because the error add up over time over many shorter steps. But in a symmetry protected simulation, the leakage remain a constant. And in this case, we chose the leakage randomly. We chose the symmetry protection in a random way. And we note that this leakage can be suppressed even further if we had chosen this symmetry protected simulation in an optimal way. We can also make some rigorous statement for the symmetry protection error. And for the purpose of this talk, I'm gonna provide a simplified version of the statement. And in particular, we assume that the Hamiltonian has 2 terms, A and B. And we're gonna simulate the evolution of this system by breaking time into many small time steps and evolve under each time step and simulate each time step by a circuit C delta T. That is basically an evolution under A first, and then the evolution under B. For the symmetry transformation, we're gonna use a unitree UK that has a special form. It is some U0 to power K, where U0 commute with the Hamiltonian. The reason why we choose this unitree UK will be clear later. Given these assumptions, then we can prove that the error of a symmetry protected simulation will be upper bounded by this quantity, where the lowest order, it is just the commutator between AB, average under the unitree transformation. You can also notice that if this UK are just identity, that is the case in a raw simulation, then we recover the commutator error, the commutator form of the error in a standard shorter simulation. But you can also notice that if we choose this UK in a smart way, we may be able to average out this commutator and end up with a next order error. To prove this statement, we basically have 2 steps. In the first step, we're gonna show that the evolution under this circuit C delta T can be generated by some effective Hamiltonian HF. And this effective Hamiltonian, more importantly, we want to show that this effective Hamiltonian, it has the form of the original Hamiltonian plus a term that proportional to the commutator between the terms of the Hamiltonian. After we get this effective Hamiltonian, we're gonna sandwich this effective Hamiltonian in between the symmetry transformation. And from the first term to the second term here, we just move the unitaries to the exponent. But then we want to show that this product of exponential can be approximated by an exponential of a sum of the terms. And you can also notice that this is very similar to choterization. But if we were to use the standard choter error analysis, we wouldn't have been able to get this error bound. And I will talk more about that later. So now for the first step, where we want to show that the circuit that approximates the evolution can be generated by this effective Hamiltonian. We first do a direct differentiation on the circuit C delta T and show that it can be written as the time evolution of a time-dependent Hamiltonian. So now it is with T exponential here is the time order exponential. And this time-dependent Hamiltonian is basically the original Hamiltonian plus a term that proportional to the commutator between A, B. After we got this step, we basically found the time-dependent Hamiltonian that generate the circuit C delta T. But we want to turn this time order exponential into a regular exponential. For that, we're gonna use the Magnus expansion. And in particular, this Magnus expansion say that if you are given a operator G that satisfies some condition, then the time order exponential of this operator G can be written in the exponential of a sum over some omega. And there's formulas for how to calculate this omega from omega 1 to infinity. So we're gonna do that for this time order exponential. For the first omega 1, it is basically just the average of this G over time. And after we do this integration, we can show that omega 1 is basically the original Hamiltonian plus the commutator. But now we have this factor 1/2 in front of the commutator and plus the higher order terms. For the higher order omega, for example, omega 2, we just need an upper bound on its norm. And in particular, we can show that omega 2 is upper bounded by delta T cube. And similarly, omega cube is upper bounded by delta T to the power 4, and so on. And that's enough for us to show that the effective Hamiltonian that generate this circuit C delta T is basically the original Hamiltonian plus a terms that proportional to the commutator between the terms of the Hamiltonian. And that is the first step of our proof. In the second step, we're gonna show how to combine the exponential into one exponential. And as I mentioned earlier, this step where we move, where we approximate the product of exponential by an exponential of the sum over the terms of the Hamiltonian. It is basically a choterization. So we can use some standard choter error analysis to estimate the error of this approximation. But in the standard choter error analysis, the error will scale as will be upper bounded by every possible commutator between the exponent that we want to combine. And in this case, we have roughly R squared of those exponential. And that's why the error will be upper bounded by R squared times delta t squared, because this is second order error. And the leading contribution to this commutator will be roughly the norm of V, assuming that the norm of H is just 1. And now the norm of V is, remember from the previous calculation that the norm of V is of order delta T. So this error will be upper bounded by R squared delta T cube. And that's why we get the error T cube over R. But this is not good enough for our purpose. So we're gonna use something else. And in particular, we're gonna use the assumption that the symmetry transformation UK is some U0 to power K to arrive at the tidal bound. Now, this special form of the symmetry transformation, it reminds us of the kick in quantum control, where you evolve your system for a little bit, then kick the system a little bit, and then evolve a little bit, and then apply the same kick to the system, and so on. And when we apply this kick in between the evolution, what happens is that it will project the simulation, the state of the system, onto subspace that are defined by these unitaries U0. And in particular, the subspace here corresponds to the eigen subspace of U0. And because we choose this U0 to be part of the symmetry of the system, this subspace will also correspond to the symmetry subspace of the system. So basically, we are projecting the evolution onto the symmetry subspace of the system. There's a bound for the difference between for the approximation in this arrow here. And for example, the bound by Bergat and others in 2019, it gives a bound on this basically symmetry protected simulation and the evolution under the Zeno Hamiltonian. And remember, the Zeno Hamiltonian is the projected version of the Hamiltonian onto this symmetry subspace. But this bound has an undesirable feature that is increased exponentially with time. In our paper, we improve this bound in a more general setting to a bound that scale only a polynomial in time. And from there, we get a tidal bound on the simulation of the on the simulation error in a symmetry protected simulation. And for example, here you can see that V is of order delta T, and delta T is just T over R, and that's why we get the error T cube over R squared. And that's basically the second step of our proof. And in summary, we propose a scheme to protect digital quantum simulation against symmetry violation. And in this symmetry protected simulation, the error of the simulation is replaced by an average version under the symmetry violation, under the symmetry transformation. In order to show these results, we show how to compute the effective generator of the circuit that correspond to the quantum simulation algorithm. And in particular, in this case, it is the circuit that correspond to the product formulas. And we also provide a tidal bound for the quantum Zeno effect. We also consider more applications in our paper. So if you are interested, please check it out. Finally, I would like to thank my collaborators, Yuan, Dan, Carney, and Jake Taylor. And thank you for your attention.